Hello, everyone. My name is Joris Peels. I'm the Executive Vice President of 3dprint.com, and I'd like to welcome you to this webinar. And it's a webinar about how advanced metal additive manufacturing can provide the space industry with a galaxy of innovation. At the moment, we're witnessing a true renaissance in the space industry, but now it's not countries, but it's companies. It's a new space race. There are over 300 companies right now vying for their place in space, up from about 12 only 10 years ago. This is a hyper-competitive race where billions of dollars and a lot of the smartest engineering minds in the world are up against each other. And they're all trying to make lighter spacecraft that go further, better propulsion units, better integrated components. They're trying to get to market faster, and they're trying to out-innovate each other. And all these firms, or almost all of them, use metal additive manufacturing to design, test, and out-innovate, to get parts to market, to get parts in the sky faster. But what's happening in metal additive manufacturing? How are these companies, utilizing this technology? And what can it do for them? And what could it perhaps do for you? Now, to learn more about that, we're going to talk to two gentlemen, Ali Baghchehsara, and he's the founder and president of Plasmos, and Brent Hansen, who's a technical business development manager at Velo3D. And we're going to tell, mainly, we're going to tell Ali's story, and we're going to tell a little bit of Brent's story from Velo's perspective. And hopefully we'll try to, give you some up-to-date, useful, actionable information for you to use to see that if this is the right technology for you to explore. So first, a little bit about Ali. Ali is the founder and president of Plasmos. He's a space entrepreneur and a corporate leader who's had a number of startups under his belt already. In automotive and cognitive science and aerospace. He's been recognized by the Royal Aeronautical Society and the American Society of Mechanical Engineers. And he's started 3 businesses, very different businesses, and also his own VC fund as well, to fund companies that other people won't touch. And he's also designed an autonomous system for distress tracking for an Airbus, a commercial Airbus, for commercial aircraft. He has a Bachelor of Aerospace Engineering and Master's in Aeronautics and Management. And he's trying to build Plasmos. You'll hear a lot more about Plasmos from Ali, but essentially they're trying to make interplanetary travel and in-space transportation a reality in a kind of more cost-effective, more frugal, different way than others are doing. So you hear a little bit more about him later. From Velo's side, we've got Brent Hansen, and Brent is a technical business development manager. He has an awful lot of experience in additive, which is very uncommon, really. He started, he worked before as a manufacturing engineer at Lockheed Martin Space Systems. Before that, he was a design engineer at NewSpace, which is a medical device company that does spinal fusion, things like that. And before that, he was an application development engineer at General Atomics. So Brent has a very deep understanding of additive, but a deep understanding of how to apply additive to very different industries and very critical industries, whether it's in your spine or in your UAV. To get there, he took a manufacturing engineering technology degree from Brigham Young University. And Brent, in his free time, likes playing with his kids, mountain biking, surfing, and spending time outdoors. Where does he find the time, people? So I hope you really enjoy this. And what we're going to do, just a little bit of order, you can ask questions of the panelists in the chat, and we will get to them. We may not be able to get to all questions. What we could also do is get to those questions offline. And there's ways for you to get into contact with Velo to ask your questions directly if you would want to ask questions that you don't comfortable asking in a public chat room kind of thing. So we'll take those questions at the end of the session. What's going to happen now is that both gentlemen are going to present to you some slides, and we're going to go through that. And then at the end, we're going to do a question and Q&A session. We're going to have some time for that. So whenever you have a question, you can put it in the chat, and then we'll get to that in the back. And thank you for your participation. Thank you so much for being here today. And over to you, Ali and Brent. Over to you.
Thank you so much, Joris, for the introduction, and I'm super excited to be here. Really glad for this opportunity to chat with everybody and with Ali. And first, I'm going to take a minute to walk us through some of Velo3D and why Velo3D is participating in this type of forum, as well as a large player in this new race, new space race. 1 sec, I lost control here. There we go. So Velo 3D was founded in 2014, so we've been around for a little bit now, but we're still relatively new in the metal printing space. We are publicly listed on the New York Stock Exchange and have been for a little bit over a year. And what we bring to market is a new technology that enables customers to print the parts that they are interested in printing with less compromise, no compromise is what we like to call it. And we deliver very highly complex, high value parts, and we have support and service worldwide. Some of our customers are definitely, in this new space realm. We have a number of machines as well as contract manufacturers, and what you see here are just some of the customers that we've worked with over the many years of our being in operation. On the top there, you can see SpaceX and Hermes, Plasmos, as well as Astra and Launcher, and various other customers here. And it's been an amazing experience working with some of these customers and seeing how they're applying additive manufacturing technologies to their products to enable space exploration. Velo really opens up a new category of metal additive parts. And what I mean by that is we enable complex geometries in ways that have not yet been seen before from other traditional additive laser powder bed fusion providers. And a lot of our parts really excel in the realm of heat transfer as well as fluid flow and fluid and cooling and other aspects of general mass movement. You can see a number of our example parts here. This top right part is one that has been widely publicized from launcher space, and it's definitely something that has been a really great application of the Velo Sapphire technology and how we can build the inside of that part, that tank, without any support material. There's a number of barriers to NewSpace AIM adoption. Maybe Ali can pitch in here as well. But some of those adoptions have been long lead times, as waiting for traditional manufacturing methods to achieve complex geometries and complex parts has definitely slowed down a number of companies in their product development iterations. And so bringing additive manufacturing in play here, you're able to rapidly iterate. If you have your own machine, you can go through rapid iterations of new geometries in a very short amount of time. And then even if you don't have your own machine, you're using something like a contract manufacturing network, your speed to market is still greatly increased, and you can come up with complex parts that really enable performance in ways that you have to really think outside the box to see basically all the different ways that additive manufacturing, especially with the Velo system, and how it unlocks complex geometries and how that can bring your product to the market faster in lighter weight, more complex ways. What are your opinions on this, Ali?
Yeah, so first of all, hi everyone. Glad to be here. Brent, thanks for having me here. And you're absolutely right. Basically, complex parts, long lead times are part of the problem. On top of what you have listed here, I would also add that from ideation to conception to creating something in hardware has been always a very, very long journey for startups. And so when we partnered together with Velo, we really realized that we can go from conception to ideas, do analysis, and then from that time on to manufacturing something, testing it. That time was a lot less. An example of it is what we have achieved over the past 1 year at Plasmos, is that we came up with a completely new type of propulsion system, which is a hybrid system for inner space transportation. And from ideation until analysis and testing, it took us less than a year. So that's an example of how it can really decrease the lead times, also go through fast iterations. And on the complex part, I'll add a little bit more throughout my presentation on the engine and also both the spacecraft. And on top of this, I would also add that it really allows us to think outside of the box of what we could manufacture. Today, we have engineers that say, this is the design, it may look weird, but we wanna give it a try and manufacture it. And we work then with Velo closely to understand how we can make a printable part out of that design that we think is optimal for operations. Back to you, Brent.
Precisely. Thank you, Ali. So where's the opportunity here? The opportunity in the new space race is what is being called at this point is, over 1,000 different companies are in this realm, and that's in the satellites, new launch systems, propulsion systems, services, spacecraft, and various antenna systems. And the funding is there at this point. We're looking at $40+ billion a quarter and somewhere around $400 billion a year. And so the opportunity is ripe, and it is definitely something that we're looking forward to working with and enabling to optimize basically how people are achieving this new space race. Where does the opportunity fit for metal additive? And as we mentioned before, it's with faster iterations, more complex designs, improved part performance. This is one that really hits home with me. Everybody thinks of traditional design for additive as your 45 degrees and all the different restrictions that additive might have. And at Velo, we'd like to enable people to the point where they can design what they want and what they want to use in their spacecraft, for instance, without worrying about all those different restrictions. There's definitely a saying that with additive, complexity is free, and there's a lot of caveats with that statement. And we definitely reduce the amount of caveats to what geometries you can and cannot achieve. So let's dig into how Velo enables that. So with Velo, we have a full technology solution here, and we're really a technology provider more so than just a machine manufacturer. And for starters, our flow software is where you bring in your native CAD and you walk your part all the way through to the point where it's sliced and ready for the printer. And in this flow software, you can assign various different parameters to automatically assign or assign regions of your parts to get specific laser parameters to achieve what you want. Now, Flow does a pretty good job of recognizing these parameters from the get-go. Sometimes you may want to apply overrides to ensure that your geometry comes out as clean as you want it to. There are dozens of these different recipes, and that is growing as we enable more and more complex geometries. And this software is built to be able to identify these regions. It's really slick. I really enjoy working in Flow compared to some of the other softwares I've worked with in the past. And the ability to rapidly and quickly select these various regions is definitely special to work with. Our printer family consists currently of 4 sizes of printers. We have 2 base build plates, the 315 millimeter build plate of our Sapphire system, and then the Sapphire XC has a 600 millimeter build plate, and those come in 2 different heights: 400 millimeter for the small machine and 1,000, and 550 and 1,000 for our larger machines. So that's 600 by 1,000 millimeter build volume in our larger machine. Makes it a very large machine with 8 different lasers. So you've got 2 1 kilowatt lasers in our small system, 8 1 kilowatt lasers in our large system. And we operate in an argon environment at a 50 micron layer. And our machines they have automated calibration functions. So where this comes from is our company, and many of our original engineers and current engineers came from the semiconductor industry. And if you're familiar with that industry, there's a high value in quality, repetition, reproducibility, and the ability to understand exactly what's going on in your system at all times. And that's something that we do in our Velo system, in our Velo machine, very well. That leads into our Assure Quality software, as I mentioned, from the semiconductor industry. The Assure Quality software is the first software that I have seen that allows you to monitor your system, your machines, and many machines at the same time, click on them, see how they're doing, see how they're operating, see what the status is, look at the height map or the image of your build. As you see in the middle, the gray picture there is the picture that is taken between every layer, and then the height map image on the right, which is actually a structured light scanner to verify that everything is going according to plan. Now, the actual Assure software also spits out a build report at the end of your build that is a 7 or 8 page document. It's very easy to look at and digest, and is a major breath of fresh air compared to a 10,000 line item text document that I'm used to seeing in the past. Production ready materials, we have a number of different production ready materials. And when we say production ready, we mean that the geometries that we advertise and we talk about can be achieved in these alloys. So we're constantly developing new alloys, and it's somewhere between a 3 and 6 month development period, depending on which alloy you're looking for. Inconel 718 is definitely one of our highest runners. And the GR-COP 42 material that is making a lot of buzz lately is definitely something that has been of great interest to me. Supporting the Southern California region and seeing how my customers are using GR-COP 42 in new and novel ways. We're committed to every customer. We have a group of applications engineers, field engineers, and technical sales engineers who all work closely hand in hand with our customers, regardless of if they're buying a printer or not. And so definitely one thing that I would advise is feel free to reach out and see, how our solution may work on your project or your problem. One thing that we also do is we do a lot of ROM analyses. And so if you want to send over your part after an NDA is signed, we can take a look at your part and give you an idea of how much that part will cost in if you were to purchase one of our printers, or if you were to use the contract manufacturing network. And along those lines of using the contract manufacturing network or your own system, we pride ourselves in this ability to create what we call the golden print file. The golden print file is basically, if we rewind a couple slides to Flow, the software, when Flow slices your part, all of your laser parameters and instructions for the tool, for the machine, are inside of your build file. So that build file, print file, contains all the toolpath for the laser, all the operating conditions, and everything that is needed to make your part. And if you take that golden print file and you put it on your machine and you build a part and you're happy with it, you can then offload production to the various contract manufacturers with the exact same build file, and it will be repeated every time. So that really opens up a supply chain, or it really clears a lot of hurdles in the supply chain. What that allows you to do is take the golden print file and shop at 4, 5, 6 different contract manufacturers with that build file and get their lead times and prices and expect the same results. Now, there are different ways of qualifying vendors, and so we can definitely take that discussion offline if that is something of interest to you. Traceability really does start with the print file. And so with all of the parameters being contained in the print file, as I mentioned with that golden print file, you don't have to worry about sending your part to somebody else, letting them apply their own support, letting them apply their own laser parameters, and then ending up with a part of either inferior strength, superior strength, or geometry that doesn't come out in the way that you expect it to. And that is really something that keeps you from being locked into one supplier at one location with one machine. And it just really allows, especially in the defense world, to get those multiple quotes that you're looking for to satisfy your purchasing, your supply chain group's desires and needs, and really unlocks rate production, even if your one supplier that you've been working with is overwhelmed or something like that. And we have a simplified qualification solution, which allows you to, get to those production parts even faster. And that's with some of the material data that we're developing with MEPDS and NAE's work and ongoing developments there, as well as the printer calibration and being able to trust what you're getting out of a Sapphire system compared to another Sapphire system. There are many keys to meeting your milestones, and our system really enables you to focus on your solution and not the manufacturing portion of your part, the process. And as you saw in some of the images below and some things that you may have seen floating around, we do enable the most advanced aerospace geometries. And that is all thanks to the system and the technology that we have developed. If you're interested in how we enable those things, please feel free to reach out and we'll schedule a discussion to walk you through exactly what sets our hardware and software apart from our competition. Ali, we'll turn that back to you.
Thanks, Brent. It was interesting to see your presentation, especially where you mentioned from concept and the golden print file. And I remember those conversations exactly a year ago, or maybe a year, 2 months ago or something like that, where I came to Velo and said, got this idea, said to me about the golden print file. And happy to present you where we are today. So let's see, Control P spacecraft. This is an idea where I think many of us have seen. That's how I see it. Maybe that's because I have dyslexia. I think of it as when you have an idea of a spacecraft and you think of it and then you can print that. That's really an awesome technology to have, not only from Velo, but in general, additive manufacturing that many other aerospace companies have developed. Having said that, now, to our spacecraft and the problem we are addressing specifically with the laser focus we have is where is the addressable opportunity. So if you think about over the past decade or so, from 35 satellites launched per year to space, now we are around about 1,700 satellites in 2021. That is that's close to 50% growth in this market. And that's not just something that you see in every other industry. That's an industry that is going to require a lot of new technologies. That is an industry that is going to face a lot of new challenges, such as the space debris. And mobility is becoming more and more an issue that a lot of startups, also prime companies, are focusing to solve. Now, having said that, there are different angles to solve that problem. Some companies are coming up with new propulsion solutions to solve this problem. Some companies like ours are coming up with a tug solution, and some other companies are coming up with ideas where they want to carry satellites, they want to monitor the space, LEO, MEO, and geostationary orbits with different technologies. And so there is going to be a lot of new opportunities that we can't even imagine at this moment, but it's going to be a reality pretty soon. Having said that, we want to think when this number of satellites are increasing in a specific orbit, like SSO specifically, how can we ensure that satellites can get to their final orbit as efficient as possible, but also in a cost-effective way? The reason we talk about cost-effective is that LEO satellites are often made a lot cheaper than geostationary and MEO satellites. They have a much faster turnaround time in their manufacturing production, and that actually means for them to get to their final orbit, they are not really ready to pay a couple of $1 million on top of what they have to pay to get to space. When we understood this problem, we really had a lot of discussions internally to understand how can we address this solution that is differentiated. And of course, at that time, we were closer to our propulsion technologies, testing phase, and we thought, well, with a propulsion system, we can help a little bit, but that's not going to be enough. So we decided to go and build a reusable spacecraft because we understood this is what is needed to meet the demand because of reliability and the costs that is, mainly the target for our customers. So introducing our spacecraft Comet, which is actually, we are working with Velo at the moment to prepare that golden 3D file that Brent just mentioned. We are maybe a day or two away from that in the last steps of that. Essentially, the idea for our spacecraft is to have to be part of one of the commercial launch vehicles. We just gave an example of Falcon 9 rideshare here for people to understand what is it exactly we are doing. We have two technology pieces into this. One is actively cooled heat shield, which is enabling us to target 10 times reusability, and a dual mode engine. I'll get to the dual mode engine in a little bit, but one thing that is really amazing to understand is that everything you see in this picture on the spacecraft side is what is coming out of a Velo printer. So almost 85% of a spacecraft that we have designed is printable. And that's, I think, enabling us also to target very new coming markets, such as tactical maneuvering, tactical response, and sometimes when there is a need for a faster spacecraft to be very quickly in manufacturing, and so printing it is one of the solutions. The secret sauce for why we can bring a spacecraft that is in orbit that has never been done before, I think that's noteworthy to mention. There has been rockets such as the SpaceX coming back to the Earth multiple times, but they haven't been into the orbit. So one thing that we had to come up with was essentially the piece of technology that we were working on, as I mentioned before, is a dual mode propulsion system. Alongside Air Force Research Laboratory and a few other primes and companies in the startup round that have been working on, I think we have been advancing much faster than many of them to get to a propulsion system that has been tested both on the chemical side and plasma system in the same engine. So now remember, this is one engine that can operate in chemical propulsion mode, which is designed for re-entry. So that's what is used to push the Baghchehsara away from the spacecraft, while the spacecraft is also being actively cooled, but also in a space operation mode, it's using a semi-plasma mode, which is very efficient. So we can maneuver, we can take satellites to their specific orbits, deploy them one by one to specific orbits they want to go to within LEO, and then start or deorbiting and re-entry process, which would mean for customers, they don't have to pay for an entire spacecraft to get to their final destination. And this engine, by the way, is also manufactured in a Velo machine. So one of our next steps is that we have a demo day for spacecraft. The date of that is outdated, so we have to change that. It's going to be on the 11th of November, where we showcase our spacecraft, its cooling system, navigation and controls demo system will be in there, and also the propulsion system will be showed, or the tests of that will be showed. And so afterward, we will do intensive testing. We will have a drop-out testing from an aircraft to check how the landing process will work, hopefully within this year still. And so to get for us ready to launch next year or latest January 2024, our first spacecraft to the orbit. Why 3D printing makes sense? All these dreams and ideas that I mentioned before, and as Brent was mentioning, is not only the geometries, but also that. But if you look at the spectrum of problems that we are facing, we have high voltage in our system. We have to have magnetic fields, means a lot of coils that has to be inside some of these engines. If you remember the picture of our engine, it looks fairly simple from the outside, but that's definitely not what's going on inside the layers of that engine. We have extremely high and lower temperatures both in the spacecraft and also inside the engine. Remember, our engine is not a normal one. So we have plasma in one operation mode, in another operation mode, we have chemical. Both of them have to be cooled in different ways. And that also means we have different layers, and that would mean a very high weight. Which we had, by the way, in our first engines, but now we are optimizing for that after we realize the functionality is not really a problem anymore in some of the functions that we designed for. So when you look at this spectrum of problems and you want to get it as low weight as possible, you have to deal with electrical, let's say, currents passing through different layers with different voltages and currents. And you have to also deal with cooling systems, whether they are active or they are passive, or different layers going on inside each other. That's when you start to realize, also given the fact that you have to build a smaller spacecraft because your center of gravity has to be within a very, very low limit so that you can carry multiple satellites inside the Reicher, you really have not so many options. And so I think it's not only that Velo has been an advantage for us, I would say it has revolutionary for our system to be able to really get here, not only faster and better and cheaper, but also really to get here at first place. So I don't know, Brent, if you have something to add here as well, and thoughts from other applications that come to you for.
Yeah, I think you hit the nail on the head there, and you actually had my brain going in different ways of things that may or may not be possible with printing. So something we can definitely take offline.
Sure. So this is our CLEPS engine. As you see on the top part, there are basically the sources for electrons, and it's, of course, this is not the first version that we printed. This is something similar to that. The injectors and spark plugs that are showing here, it's partially chemical, partially chemical, but as I mentioned, all those four problems are really addressed in one simple print, which is addressing the cooling systems, the magnetic coils, different magnetic coils going on in here, and all of that looks very simple when you look at it from outside. I think this is pretty much it from my end. I think we can allow the audience to ask some of their questions, and I've seen a few questions already.
Yeah, Joris, do you want to?
Hey guys. Okay, so thank you for that, guys. Thank you so much for that. Okay, so first off, I have a question. I mean, I think if we're looking at getting the new geometries faster, because that seems to be what a lot of people are saying, like, you know, people may still believe that the you know, conventional manufacturing, things like CNC, well-tested technologies, they understand casting could feel more comfortable, but you know, can we quantify a little bit, give people a little bit of an idea of what it means when we say that additive is faster to getting the new parts?
Yeah, for sure. So there's a lot of different factors to consider. One is your company focused on process qual, or are they focused on part qual? That's a big portion of it. If you're focused on process qual, things take a little bit longer in general, and that's been over the history of manufacturing. If you're focused on part qual, and you can basically, if you have the ability to set up a test stand or whatever it might be for your part, and then rapidly make a part, test it, alter it, make the part, test it, alter it, until you start hitting whatever your proof loads might be. That is where true speed is enabled, and we can see people create new parts and new applications in a very short amount of time. But with that being said, you're sinking money into a part qual where you could be sinking that into process qual and then enabling 20 different parts in the future. So there is a trade-off.
Mm-hmm. Okay. Thanks.
Real quick, just to add to that, sorry.
Yeah, sure.
One thing that I would add is that typically people's creativity and CAD skills are the limiting factor there. So we see people that come up with, you know, they come to us with geometries, and I throw out 4 or 5 different options of what they could be doing with their part. And then they'll come back with a geometry that looks almost exactly the same, but maybe there's like a little pocket for lightweighting. And it's like you're missing the point. You have to remove all of your knowledge of CNC and everything else that you might be familiar with, and think, what do I really want, and design that.
Yeah, I think that's a really great point. What I've seen with clients is sometimes they look through it with one lens and they have like one advantage. But if we look at some applications that are really making sense, for example, the rocket propulsion and stuff like that, we often see there's like maybe 8 to 10 advantages in the individual additively manufactured part, as opposed to the, whether we get different modulus, different texture, different whatever. There's lots of different changes.
Right.
Okay, so Renee Cooper would like to know where the contract manufacturing services are performed. So that's a bit of a trick question, because like you guys got a network of people that you work with, right? They're all over the place, right?
Mm-hmm. Yep. So Vela doesn't actually make parts for people. We don't have the quality department set up for producing additive parts. That's not what our goal is. So as we work with these contract manufacturers, there are several of them, and there are more coming online. Currently, there are none in the Southern California or California region. Most are in the Midwest, we'll call it. So Texas, Oklahoma, Illinois, things like that.
Okay. And what I always think is really interesting about you guys, these companies are sometimes like oil and gas companies or the aerospace. They're really manufacturing companies rather than like a 3D printing service, right?
That's correct. Actually, all of them started as a manufacturing company, where they have traditional CNC welding, whatever it be, capabilities, and then they onboard the Vela technology.
Okay. And this is, I think, a question by Craig writes, how are each of the machine's nuances dealt with when printing a golden file to achieve the same accuracy and properties? How do you deal with run-to-run differences for the machines?
Yes, this is a very good question, Craig. It is one that is incredibly protected IP for us. So you're welcome to reach out, and we can have a discussion offline, especially under NDA, and we can go into more detail. It's something that is so simple, but it's so unique to us.
Can I guess? No. No. Okay. So there's another question is, well, there's two questions actually by the same individual, Jim Vasher. And well, what is the most important criteria for proving powder metals using AM? That's actually, well, that's quite a beast of a question actually, because, well, there has to be a market for it, and there has to be demand for it, and people have to be able to make it for a long time. But yeah, so it's a bit of a difficult question, but try to have a stab at it there, Brent.
Yeah, so this is definitely a multifaceted question. The one thing that I focus on personally as an engineer, who's been through qualification of multiple different parts and multiple different industries, for me, the most important part is chemistry. Right. So the most important criteria is making sure that your chemistry is what you want it to be and what you expect it to be. And then there's a lot of other considerations there, but I have found that, and this is through years of experience, I have found that you can test the powder as much as you want. You can continue to sink cash into your powder over and over again. Or you can just test the parts that you're printing and ensure that you're getting what you want in the parts that you're printing, be it, through witness coupons or tensile bars or compression coupons, whatever it might be that's appropriate for your industry. But as far as the powder goes, I mean, there's all the considerations about it working properly in your system and whatnot, don't get me wrong, but the chemistry is what, in my opinion, affects your final part the most in the end.
Okay. And then, yeah, the same, Jim has another question, like, are there any factors in the metal powders that you would like to see change in a broader array of parts, like with lower oxygen or something, or more sphericality, or but to a certain extent? Or,
I'm not sure, honestly. It's that's another interesting question. I don't really have a great answer for that. What we could be improving there, with like titanium, sure, starting with lower oxygen would be great. But at this point, most of the powder manufacturers can support whatever your request is on the oxygen front.
Yeah. Or a new generation of materials like ODS steels, but better than Inconel.
Better than Inconel. Yeah, I mean, at this point, it's, if there's a demand for it and people are interested in printing it, more than interested in printing, if they're interested in, partnering with us to develop that material or purchase a machine in said material, it'll get developed. So we're not necessarily in the business of making alloys, though.
Okay. There's a really interesting question for Ali here. That's the last image of the Plasmos. Somebody's been paying really, really close attention to the image. The last image of the Plasmos engine shows seemingly common spark plugs. Are these only used in testing, or are they intended for orbital use? Is there a pre-combustion chamber that these plugs spark into, a bit like in some internal combustion engines? And if so, did such chamber design take advantage of the additive or velo capabilities?
Good question. This is actually just demonstrating that there are spark plugs. Otherwise, we are using an NSI spark plug. So it's just demonstration. That's a picture, not a real engine, as I mentioned.
Yeah. So one thing that's a bit commonly held secret is that a lot of these geometries, and especially if you see cutaways of engine parts and other parts, they kind of get like the new kid or the intern to make like a fake one.
Right.
And that's the one that ends up on the stand in a show, or that's the one that ends up in. So if you think that sometimes these things look really cool, sometimes the actual engine is not actually the one you get to see. That might be I don't know. I'm not saying that's a question here, but that happens a lot in additive because people want to protect these geometries.
Exactly.
So another question I think for Ali, how did you actually end up, turning to additive? I mean, was it like, did you get stuck, or was there no other way you could do without it? Or was it just like, well, everybody's doing additive? Well, how was that path for you?
Yeah, so before starting Plasmos, actually, or the prior company to that, which was called AB360 Space, that we renamed later on to Plasmos, I was maybe for about 4 or 5 months looking into different additive technologies. So I was looking at some of the velo competitors and looking at how it helps with metal. And essentially the reason for that is what I explained earlier in the slide. So the complexity of the engine, when we started concepting how this concept is going to work, when we want to put two types of propulsion systems that both separately have been used in a space for years, we very quickly realized this is going to be a very complex geometry. We are going to have challenges that other engines don't have. So when you think about that, you essentially start to think, well, even if I design something like this, then how am I going to manufacture it? And in fact, one of the early advisors we had in the company who has worked on a similar technology in 1996, with an ESA project, they were trying to figure out how they can do a combined engine, and they essentially didn't get to it because of the thermal complexities they had to deal with. Now, thermal is one of them. I also didn't mention a few other things like corrosion, erosion that can be solved again with specific geometries such as foams. Those are again things that using normal system you can't really get to. So this is, it's not only one problem that we say, oh, we have this curve here, we can't really do it on normal machines, let's go to additive. And then after we started working with Velo and they invested in us, we were actually talking about that on a podcast with your CMO, and I mentioned, we are basically like a family. So Velo became more or less like our manufacturing department in some ways. So we think of it as a technology enabler when we are thinking, a spacecraft production, for instance, was not part of our business at first. When we started an engine, we were an engine making company. But then when we realized the problem, and we said, well, we have to manufacture a spacecraft, and we got through the first iterations. We were like, we don't want to use heat shield, and then we went to active cooling. We're like, wait a minute, we have additive manufacturing. How can we size that? How can we design it? And we were like, yeah, this is possible. So it became more or less a possibility and became an enabler for anything that we imagine to make it a part, rather than let's design a part that we can manufacture and now find the technology to manufacture it, if that makes sense.
And are you guys like making all of it, your components additive now, or is it like there's still a mix of some conventional components, or is it mainly additive? Or
so it's actually mainly additive. It's funny enough, mainly additive. We do a lot of post-processing on the systems, as you can imagine. But mainly additive has become an interesting trade-off for most of the mechanical production starting about. So electronics, of course, not yet. Maybe some days.
Well, it's going to take a while. Okay, and then there's another question. I think Sasha Schenk asked. It kind of ties in the electronics. Is, what about ceramics? Now there are several other ceramic manufacturing technologies with very interesting materials, of course, very interesting properties for space. Velo, as far as I know, is not going to do that or not really looking at that soon. But there's a bunch of other technologies. It's not a very mature market, the ceramics additive manufacturing market, but there are some vendors out there like XJet, for example, makes ceramic components, and there's some other ones as well. If you're interested in that kind of thing. So another question by Larry Stewart. After a customer buys a printer, do you provide consulting to help them achieve the best result, or do you charge for this follow-up? I think with a better a question kind of for Larry is like, how does a normal customer engagement start? Because normally, it starts with the people having a problem or wanting to be curious. I mean, how does this process go, and how does it go from just the beginning to somebody getting a printer and stuff like that? I think that kind of a little bit broader than what Larry wants, but I think it would answer just as well, a little bit better maybe.
Yeah, so it's a great question, and it's something that I deal with every day. I would say that initially we start with NDA, and then we take a look at your part from an engineering point of view. So that's specifically what my role is in Southern California. So if you're in this area, then feel free to reach out. Either way, we can link you up with the right person. What we do is we first take a look at your part. We give you any design considerations or changes that might be needed, or things that could be improved. And we walk you through what that cost would be of that part. This is all free under NDA. We do not charge for this level of consulting. This, depending on, we obviously will ensure that we're working with somebody who is serious. And if they are serious, we'll continue that level of support as long as you would like. If you start buying parts from the contract manufacturing network, we continue that support. If you buy the system, like as your question was aimed at, then yes, there will be an applications engineer assigned to you to help you in any way, shape, or form that you need, as well as any other. They have access to the rest of the VL team, and they can pull on the expertise of anybody on our team to help any specific customer. That I think that we're pretty unique in this way, because we don't charge for consulting here. We don't have some crazy additive tactical team who's going to go and give you this giant scope of work and expect $100,000 PO. That's not how we operate.
Okay, all right, that's good. And then I think a question again for Ali. I mean, I think for this additive, I mean, how do you internally deal with additive is for some engineers, I guess there's a race for talent in the space race as well now, I would guess, right? How do you, get people up to speed with additive? How do you do that in an organization to try to get to work together with this technology that might be new for some, or, that might be just completely something they can't come to grips with?
Yeah, so that's actually a very good question. You wanted to add something to it, George?
No, it's fine.
So it definitely had a learning curve. So now slowly our engineers are learning, okay, so this is not printable. So if this is a conversation I had with some of the engineers a few days ago when we were going on back and forth for the spacecraft manufacturing. And so they are getting a handle of it. It's different, you can design things in a different ways, but we have been, I worked in Europe for quite some time, and came here and I had always a good network. So I think the network of people and knowing, okay, this is a person who is more creative, then they can learn that much faster. So I think there is definitely a learning curve. That learning curve, it's exponential. So at first it's very crazy because you're like, oh, this is printable. And then at the end, there is still something new you can learn that is improving your designs a little bit, but there is always something more you can do to improve your designs and understand how is this system manufacturing something. And I think one of the things I want to point out to is not only the engineer's mindset, but I also think, I don't know if this is a topic for you, Brent, or for if Velo is thinking about it at all, is that I think there is a new need for a new type of tool for designing. I mean, we have seen some of the recent developments for toolings, but SolidWorks and a few other tools that we have been, for example, using, I think they are designed for you to machine something, to use the traditional technologies. Now, imagining some of the more advanced toolings like what anthropology has designed or achieved in the last few years, I think that type of development is required in the market or needed in the market. So they kind of come together and build a new design tool so that you instantly know this is going to be printable. You instantly can design something that may not have been manufacturable in the past, but then you can really design that in a few seconds. And lab material is a great example of that, right? So those are things that if you want to do that on SolidWorks, it's going to take you probably years to do it, whereas in some other tools it can take you seconds. So I think there is, and once those tools come out, then engineers are going to learn it. You know, people who come out of the college and have the passion to learn some new tools. Additive has been one of the things that we see. Some of the new engineers or interns show a lot of passion. Oh, this is a rocket engineering position for working on 3D printer. Cool, I want to join. So it's shaping its own ecosystem in one word. I hope I answered your question, Joris.
Yeah, definitely. Okay, the next thing is a question by Brian Kopax. It does develop new material recipes and property data for properties data probably for customers. If so, is there a cost and what is the typical lead time? Are users able to develop their own recipes?
Yeah. So on this question, there's been a number of different scenarios that we've been through as a company. One is if you want a proprietary material that has not yet been developed, we will develop it at a cost, of course. And then we will not basically sell that to anybody else or let anybody else use it if it's your proprietary metal that you're paying for the development of. If it's an alloy that we haven't developed yet, say 316 stainless steel, if you want that material, then there needs to be some kind of commitment of demand, and the easiest way to commit that is to buy a system. So if you buy a system for 316, a material that we haven't developed yet, we will then develop 316 for your system, and that usually takes somewhere around 3 months, give or take. If it's a more challenging material, it could take a couple months longer. Some of the nickel-based alloys we're able to develop in a very, very short amount of time. So that covers a typical lead time there. Users, unfortunately, are not able to develop their own recipes, and here's why. The part of the secret sauce is and how Velo works and is able to print these complex geometries is that we have a much smarter laser, basically. And at the end of the day, the tool path that's commanding the laser is much smarter than just a contour and a hatch. And so we can't really allow customers to tweak their machine and the parameters because there's so much going on behind the scenes to enable those complex geometries and low overhang specifically. And then, if you think about like an Inco 718, how we were talking about the golden print file and allowing customers to print the same part on different machine serial numbers at different locations, that would break that system really fast if people were trying to develop their own recipes and tweak the recipes for whatever reason that they might have.
Okay. All right. So I have another question. I think again for Ali, I think in this sense. So you've been active in both Europe and the United States. Like this, all the funding is coming from the U.S. All the big new space companies are from the U.S. There's also some stuff happening in Europe, but not that much. What's it like working these two different things? Is it really like America's the Wild West and much larger? In Europe, it's much tinier. Is that because that kind of seems like it's that's what's going on? What is it like in between the two areas?
Yeah, that's a actually interesting question. And, I immigrated to the US about 8 months ago. So before that, I lived in Europe for about 8 years. And one of the reasons I immigrated to the US was essentially that things seemed to me that they go faster here. And now that I'm here, I see that, but I also see something else. There is a little bit of a mindset difference. So compared to Europe, people like to do things in a way that is more stable. They like to discuss things and analyze things a little bit more than people do here. So scrappy is the way that we do it here, which is not necessarily the way I did my last startup. We were more focused on doing a design that is robust. Therefore, we could service initially customers that were primes. Like my first or second customer in my last company was Airbus Defence and Space. So now that is very different. Why such a company would come to a company like Plasmos? The properties of the company is essentially different in the US. So you want to go fast, you want to develop things at a much lower cost, and you stay a lot more focused in the US, which is not necessarily the case in Europe. So there is a couple of different reasons, and I think these reasons has shown a result in the capital market, and how European startups have been able to attract capital. I think in Europe there has been that learning. People have learned, okay, how San Francisco mindset or Silicon Valley mindset is, and that is not anymore necessarily within San Francisco and the Bay Area, but I think there is number of differences. Talking about today and the space industry, I think there are a few good space companies in Europe also developing, such as south of Germany's ESAR Aerospace and few others that are moving fast. But still there is a different element that is a combination of talent and ecosystem in the US that is quite unique. So I definitely reckon that this is something I haven't seen that in Europe as much.
Mm-hmm. So, and two questions, like one is about software upgrades, the other one about hardware upgrades. So first off, are there software upgrades on all the various softwares that you mentioned? And or do we have hardware upgrades on the systems as well?
Yes, we are constantly improving. So there are software and hardware upgrades that come out periodically. The way that this works with the golden print file is that the software releases can always build older files, and so that hasn't been a problem. We've demonstrated this. We have a white paper coming out with an oil and gas company where we demonstrated pulling a file off the shelf from over a year old, reprinting it, retesting it, and showing the results over 7 different printers. So really excited for that one to be released. And then as far as hardware upgrades go, most of the hardware upgrades that I've seen so far have been on the powder handling side, just to increase the flow of the way that the powder works through the system before it goes through another recoat cycle. So yes, there have been hardware upgrades. There will continue to be hardware upgrades. And there's different methods for how those get deployed into the field.
And the idea behind this golden print file, just in case you missed it, because I'm trying to get my head around it.
Yep.
It means that I can go from not only run-to-run differences in different Velo, Sapphire, XC systems or something, but I can also go to a different model, right?
Correct. Yeah. So you can't go from a Sapphire to a Sapphire XC with that exact same file, for instance, but you can go Sapphire to Sapphire or XC to XC.
Okay. Yeah. Okay. And what's the idea of going forward? If you upgrade the system, will it be reverse compatible, or not always, or will that depend? Or
correct, it'll be reverse compatible. Yep. So there's a number of different reasons there, but at the end of the day, the in situ monitoring that we have in the system allows us to calibrate those machines to what we expect, basically. Okay.
All right. Okay, cool. One thing we did mention, a different white paper. There is a different white paper that you can download right now. Hope you can see the link. And that's how Velo 3D Metal AM is fueling the new space race. And you can download that. There's a Google Drive link that you can download that paper from, and you can then read it and use it as your reference. So do take a time to download that if you want to know more. You can also get in touch with Brent or Velo just generally through the Velo 3D website if you want to learn more, or if you want to speak privately with company and with people. And on the whole, I mean, generally, is there something that you would like to say? I mean, we're reaching to the end of our little webinar and Q&A. Something you'd like to close off with, or is there something you're like, oh, I wanted to mention that, but I didn't?
You want to go first, Ali? You want me to? Yeah. So yeah, I appreciate everybody joining today. This has been a lot of fun. I really enjoy these types of conversations. So if you're interested, as Joris mentioned, in any additional information, please feel free to reach out. There's a whole team of business development people such as myself who are happy to take your questions and work with you to improve your parts, as well as demonstrate how Velo is working in the with this golden print file, with this concept of really enabling production, as well as making it feasible for everybody.
Okay. Thank you. Thanks for doing this, Brent. Thank you so much.
Thanks, everybody. It was a pleasure today.
All right. Thank you. And thank you for being here, everyone. And we hope you enjoyed it. There will be a recording of this, and you can watch it on YouTube if you want to watch it again, or share it with colleagues or friends, things like that. Yeah, thank you so much for your time today. We hope this was helpful for you. We hope you learned stuff. We hope your mind is racing, and we kind of inspired you in some small way. And then thank you so much again for joining us today on this Velo 3D webinar. My name is Joris Peels, and this is also brought to you by 3dprint.com. Thank you very much. Have a great day.